Professor R. Ashokamani, Director for Research and Development, Dhanalakshmi Engineering College, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in Applied Electronics, which is intended to the 3rd semester students of who are doing the paper on physics of materials. We have been going through a course of lectures on the section on crystal structure. In this lecture, the contents are translational invariance, primitive and compound unit cell, and rotational symmetry. In the last lecture, I told you about the definitions of the lattice, then the other terms like basis and the crystal structure. This refers to a lattice, an ordered arrangement of points in space. With this you add a basis. A basis, I would like to emphasize, it may be a single atom or a group of atoms or ions. I want to emphasize this particular aspect. If it is a group of atoms, as it happens in the case of NaCl, you have got a Na ion and Cl ion, and so now I am specifically showing 2 atoms, atom A and atom B. This forms the basis, and where will you put the basis? Around the lattice point you have to have the basis, because you have got 2 atoms. On the other hand, if you would have got only 1 atom, what you would have done? The atom could have been placed on the lattice point itself, but if you have got 2 atoms or 3 atoms or 3 ions, then in such a case around the lattice point you have to place the atom. This is a very important point to be borne in mind. With this we can pass on to the primitive cell. As I told you in the last lecture, this constitutes what is called a primitive unit cell, and vectors A and B are called the primitive translational vectors. I told you in the last lecture also, by translating the primitive translation vectors A and B, or by translating the compound unit cell, this is called a primitive cell, right. This the area encompassed by this section is called the primitive unit cell. By repeatedly translating the primitive unit cell, you can generate the entire lattice by either by translating the primitive cell or the compound unit cell. By both cases you can generate the entire lattice, but the important point again is only the compound unit cell will exhibit all the symmetry properties or the symmetry elements of the entire lattice. So, there is an intimate connection between symmetry and physical properties, about which I will talk to you later. Symmetry is important, right. Symmetry and physical properties are important. I am showing what is called translational invariance. Now, all lattices will have the property of translational invariance. By this what I mean is, irrespective of the point you choose, the lattice will remain invariant. What do you understand by the term invariant? If you choose this lattice point, how many nearest neighbors are there? There is one nearest neighbor here another nearest neighbor below this, one neighbor here, one neighbor here, there are 4 nearest neighbors, right. Similarly, if you choose this lattice point, again there will be 4 nearest neighbors, one above, one below, and one on the left side, one on the right side. So, irrespective of the point you choose, the lattice arrangement or a periodic arrangement of lattice points or atoms, it remains the same. So, that is the reason why these are called, every lattice is said to be having what is called translational invariance, right. Now, this vector is called translational lattice vector, T is the translational lattice vector. Now, we will move on to the unit cell can be translated from here to some other region, right. So, this unit cell can be obtained by translating this cell, or the entire lattice can be obtained by translating this from here, here. So, the entire lattice can be obtained by translating the unit cell. Now, in a solid, the unit cell forms the fundamental building block. Now, if you go to the wall of the building, now these are things that I told you in the last lectures, and you have the unit cell here. Now, the unit cell, when it is repeated, you get the lattice, right. The entire lattice can be obtained by repeating the unit cell. You have the vector A, okay, and vector A can be translated along this direction, say x axis. So, you can obtain the lattice points along this direction. Similarly, you can generate the lattice points in some other direction, okay. You can have A here, A here. Now, instead of a square lattice, you got a lattice wherein a parallelogram forms a fundamental unit cell. So, you can have a vector B. By translating the vector B, you go to this atom, right. So, you go from this atom, you go to this atom, okay, or this lattice point, you go to this lattice point. So, by generating A, you go to the lattice points along the x direction. In some other direction, you can make use of them primitive translation vector B and generate and go to the other points. By translating A and B, this is the basic unit cell, right, the primitive cell. By translating the primitive cell, you can obtain the entire lattice. As I showed you just now, by translating the primitive cell, you can go to, translating this cell, you can obtain this, and by translating this, you can go to this, and by translating this, you can go to this, and so on. So, it is possible to build up the entire lattice by translating either the primitive cell or the compound unit cell. Now, because I have been telling so much about the unit cell, now let me ask the question, what is the unit cell of the wall, right. I mentioned about the wall. I am sitting in a building, brick, only the bricks make the wall. Now, you should remember, as students of material science or students of electronics, now you have the structure as well as bonding. I told you in the first lecture, the structure and bonding, the crystalline structure, as well as what is the kind of bonding you got, right. Bonding means how the electrons are distributed in the solid. Both these things decide the physical properties, not only the physical properties of inanimate objects, but the physical properties of animate or living beings themselves, right. The DNA and other biological systems. Now, the properties of biological systems, again they depend upon the crystalline structure as well as how the electrons are distributed. So, how the electrons are distributed, it refers to the kind of bonding, right. So, the important point that you should remember is the structure and bonding decide the properties. What properties? The electrical property, thermal property, electrical conductivity or superconductivity, or thermal conductivity or thermal properties, or magnetic structure, magnetic moment, and dielectric properties. So, all the physical properties, chemical, the catalytic behavior of the materials. So, the physical properties, chemical properties and biological properties of all systems are decided by the crystal structure and the way in which the electrons are distributed in the solid. Now, what is the kind of bonding you have in these buildings? Now, you have a cementing factor, right. Cement is you have to have a cement, you cannot have simply bricks one or the other, you should have some cement, so that the bricks are bonded to each other. Similarly, you have got the atoms, there should be the electrons, they give rise to bonding. So, similar to the cement, you have got the electrons in solids, they give rise to the bonding. The bonding may be metallic bonding or covalent bonding or van der Waals bonding or ionic bonding. It is depending upon the way in which the electrons are distributed. What I would like to tell you from this picture is the following. Now, this is a very elementary thing. In a elementary level, one should understand how a structure is made, a building is made. In a building, the unit cell is the brick. Okay. A brick forms the fundamental building block. Similarly, the unit cell forms the fundamental building block in a crystal. Okay. Then I will move on to another building, right, the famous College of Engineering Guindy, from where I am giving a talk. Here you can see, when you go near the wall, you can see the bricks. The bricks will be kept one over the other, they are stacked, and again the important point is I mentioned about translational invariance. Now, if you look at the cloth I am having on the table, it has got again translation invariance, which you may not see, but the point is you have got square, another square, another square, they are repeatedly placed, and so it has got translation invariance. Keyboard itself, there is a translation invariance, right, because they are, the keys are periodically arranged, and similarly here the bricks are periodically arranged. There is a brick here, another brick here, another brick here, another brick, again one over the other, right. So, from this brick you can go to some other brick by translational invariance. Okay. So, the so called translation invariance comes. Let me now define a lattice. A lattice in 3 dimensions, the unit cell will be looking like this, right. Now, what are the parameters which are related to the unit cell? The 3 axes, you have got A here, right, it is a rhombohedral kind of thing, and B here, this is a B, and this is the C axis, right. You have got the vector A, this is the origin, vector A here, then vector B here, it terminates here, vector C here, that terminates here. Okay. They are the 3 lattice parameters, right, they are called the lattice parameters. In a cubic case, there will be only one lattice parameter, because the cell dimension along the x direction, y direction, z direction, all of them will be the same. So, there will be only one lattice parameter in a cubic unit cell. On the other hand, in general, if you take a unit cell, which when repeated will give the entire lattice, you will have 3 lattice parameters like A, B, C, as I told you. A, U1 is the unit vector, similarly U2 is a unit vector, U3 is a unit vector. Okay. You have got the magnitude of the vector is A, the magnitude vector along this direction is B and C, then the angles are alpha, beta and gamma, and so for any given unit cell there will be 6 parameters, namely A1, B1, C1 or A, B, C, there are the 3 distance parameters, and the angles are alpha, beta and gamma. This is the unit cell. Okay. This can be repeated, right, this can be repeated to get the entire solid. So, what I am showing here is something like the brick in a wall, right. By translating, you have a brick here, brick here, brick here, you translate the brick, the entire wall can be made or the entire building can be made by translating the brick. The brick will have a size, it will have a dimension A, length may be A, breadth will be B and the thickness will be C. I have been repeating some of the basic points now, because of the simple reason. Now, these things are not generally very well understood, right. For instance, I mentioned about the lattice and the basis. these things, how you place the basis around the lattice point, these things are not very well understood. One should have a very clear understanding of these things, right. They are the basic things. Let me now pass on to, I told you about building, because in a very elementary way, when you know how a building is constructed, the length, breadth and thickness of the wall. Similar to that, you will be having the angles are 90. Remember, in a brick you have got the length of the brick and the breadth and the thickness of the brick. Now, the angles are all 90, but in a general case the lengths will not be equal, as in the case of a brick. The angles are important, again they need not be equal, right. In a cubic unit cell, you should know the lengths are all equal and the angles are also be equal, and they will be equal to 90 degrees. In a general case, it will be the thing, the unit cell will be looking like this. This, when it is translated, the entire solid can be obtained. Now, the question that stands before us is the following: what are the shapes of the fundamental building blocks? How many types of unit cells are there, right? How many shapes are there? That is the most important question. So, in order to have a proper understanding, we have to go through what are called symmetry operations. Now, how do you define a symmetry operation? A symmetry operation is an operation that is done on an object. After the operation is done, it leaves the system invariant or throws the system back into the original configuration or identical configuration or equivalent configuration. I make use of the following adjectives: equivalent, original, identical and indistinguishable. Now, if you take the table, now through what angle I can rotate? I am taking this as the axis. I am going to rotate the table along this, in this direction. I am going to rotate the table. Through what angle I can rotate the table, so that the table comes back to the same configuration. Remember, this is a rectangular table, right. This rectangular table will assume identical, indistinguishable, equivalent. The original configuration will be achieved when it is rotated through 180 degree, because it is a rectangle. Now, I have been talking about rotation. Now, let me summarize the various symmetry operations: rotation, reflection, inversion, rotoreflection and rotation cum inversion, right, roto inversion. I will deal with inversion at a greater length at a later period, because it has, I told you about the intimate relationship between symmetry and physical properties. All symmetry operations are important, right. Now, let me now go back to rotation. Okay. How do you define rotation operation? A rotation operation, as I told you, is an operation when a body is rotated about a particular axis. Through what angle it can be rotated? After the rotation is over, it has to go back to identical configuration. The lattice is left invariant as a result of rotation about an axis by some angle phi, right. Now, what is phi? Now, a body is said to have an n-fold rotational axis if it assumes identical or indistinguishable or equivalent configurations or positions n times when it is rotated through 360 degrees, right. For instance, a square has got a 4-fold rotational axis, or folders of rotation for a square is 4. The folder of rotation for a square is 4, means what? When it is rotated, you take a square, when you rotate a square through 90 degrees, what is 360 by 90? It is 4. It has got 4-fold rotation, means what? 360 by 4 is 90 degrees, right. So, the angle of rotation is given by 360 degrees by n is the foldness of rotation. If it is square, means it has got a 4-fold rotation. Why it is called 4-fold rotation? Every time it is rotated through 90 degrees, the whole 360 degrees you consider, if you rotate the body through 360 degrees, for every 90-degree rotation, a square will go back to the identical configuration. You take a square, every 90-degree rotation, the square will go back to the same configuration. You take the human body, you take me, if I rotate myself, right, through what angle? If I rotate myself through 180, do you see me? You cannot see me the same configuration, right. Rotate myself through 90-degree, I go to some other configuration. So, what is the angle through which I should rotate myself? This is rotation axis, right. Only if I rotate myself through 360 degrees, you can see my face, right. So, you should remember, if I am rotating myself through 90-degree, I go back to some other configuration. If I rotate it through 180-degree, you will not see my face, on the other hand you will see my back, right. So, that is not very likable. So, for a human system, the human system for all human beings or all objects, most objects, a rotation through 360 degree will take the system back to the original configuration, right. It is a trivial operation. Every system will obviously will have to come to identical or indistinguishable equivalent configuration where it is rotated through 360 degrees. On the other hand, if you take a square, rotate a square through 90 degree, it will go back to the same configuration. Take a rectangle, you take a rectangular table that I have got here. If it is rotated through 90 degree, it will go back to some other configuration, right. It will not go to the same configuration. Through 180 degree rotation only will take it back to the same configuration. So, the angle of rotation by which a object should be rotated, it is phi, that will give you, that is connected to the 4-level rotation. If it is a 4-fold rotation means it is a square. If you take this irregular object, I am irregular, right. So, if you take a irregular object like this, now what is the angle through which it has to be rotated? If it has to come to the same configuration, right, then obviously it should be rotated through 360 degrees, right. The entire thing should be rotated. This is the rotation axis. About that I have to rotate, okay, either clockwise, anti-clockwise. It has to go back to the same configuration. Through what angle I should rotate? I should rotate necessarily through 360 degrees, right. So, this irregular object, any irregular object should be, including me, should be rotated through 360 degrees in order that it goes back to same or identical, indistinguishable, equivalent configuration, right. The whole branch of mathematics called group theory, very many books on group theory and whatever I am telling about symmetry, they are mathematical formulation of the rotation can be given in terms of matrices, the group theory is the mathematical tool to understand all these operations, right. Now, you take a square, right, I am sorry, you take a rectangle, right, it has got a 2-fold rotation axis, because if I rotate the rectangle by 180 degree, it will go to this configuration, the length will come along this direction, it will not go back to the same configuration. On the other hand, if you take a square, it will have a 4-fold rotation axis, right. It will have for every 90 degree rotation, it will go back to the same configuration, but not a rectangle. A rectangle will have only a 2-fold rotation axis, right. What do you mean by 2-fold rotation axis? 360 by 2 will be equal to 180 degrees, right. 360 by 2 will be 180 degrees, or 360 by 180 will be 2. That means, the foldness of rotation for a rectangle is 2. For a equilateral triangle, what is the foldness of rotation? For every 120 degree rotation, it will go back to the same configuration. So, a equilateral triangle will have a 3-fold rotation axis, a square will have a 4-fold rotation axis, a 5-sided element called a pentagon will have a 5-fold rotation axis. Okay. Every time it is rotated through 72 degrees, it will go back to the same configuration. Okay. Now, so we have talked much about rotation symmetry. We have been talking about a 2-fold rotation axis, that means the object comes back to the same configuration when it is rotated through 180 degrees, right. Let us now look at this system, right. You have got what is called the letter mum. What is the angle through which it is rotated now? It is rotated through what angle? 90. 90 means it will come back like this, it will be on the vertical, right. Now, it goes back to the same configuration, the word, the letters mum, right, the word mum, it goes back to the same configuration when it is rotated through what angle? 90 or 180 or 360. You see the 180, right, mum goes back to mum, right, it is getting repeated when it rotates through 180 degrees, that means 360 by 180 will be 2. So, these words that you have here in front of us, mum, it has got a two-fold rotation axis. On the other hand, you take a equilateral triangle. Now, what is the fold of the rotation of a equilateral triangle? An equilateral triangle will have a three-fold rotation axis. Here, this one will not have a three-fold rotation axis, right. On the other hand, this one has got a equilateral triangle, right. Objects that repeat themselves upon rotation of 120 degrees, right. 360 by 120 is what? It is 3. 360 divided by 120 gives 3. So, that is reason why you say this object, namely the equilateral triangle, has got a three-fold rotation axis. The square will have a four-fold rotation axis. You have a square here, right. You have got a lattice which has got the lattice points here, right. It is a square lattice. Remember, it is a square lattice. That is the reason why only a square will have a four-fold rotation, right. Rotate it through 90 degrees, you get this, right. You rotate it again 90, again 90, one rotation, second rotation, third rotation, fourth rotation, right. So, when you rotate it every time through 90, you do not know whether it has been rotated at all, right. What is the difference you find between this and this? You do not find any difference. That means, a 90-degree rotation does not make any difference, because this is what you get now after 90-degree rotation is the same as what you had prior to rotation. So, 90 plus 90 180 or again 90 being added 270, again this is 360. So, 360 divided by 4, that means 90 degrees, or 360 divided by 90, that has got 4. 4 means what? It has got the foldness of rotation is 4. So, every time it is rotated through 90 degrees, it goes back to the identical or indistinguishable configuration. Now, let me go to the summary part. All lattices, as I told you, have the property of translational invariance. Both primitive as well as compound unit cells can be used to generate the entire lattice, but the point is only the compound unit cell, it will alone exhibit all the symmetry properties associated or the symmetry elements associated with the entire lattice. The primitive cell will not give the entire lattice, only the compound unit cell will give the symmetry elements of the entire lattice. Then the other points we discussed were the rotational symmetry. Now, a system is said to have an n-fold rotation axis if the system goes back to identical, indistinguishable, equivalent configurations, if it rotated through n times in 360 degrees. Okay. The whole 360 degrees, if it goes to the same kind of thing n times, the system is said to have n-fold rotation axis. Now, let me go to the questions associated with this lecture. The question number 1 is, what is a symmetry operation? How do you define rotational symmetry? What is the fold of the rotation of a equilateral triangle? What is the kind of symmetry in the word symmetry? I am showing again in the word symmetry. I am asking the question, what kind of symmetry you got? Does it have a 3-fold rotation axis, or does it have a mirror reflection? Does it have inversion center? So, what kind of symmetry you observe in the word mum? With this we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.